Okay, May, June 2023, variant 42. Found the paper.
Okay. Yeah, this one we did last week.
Okay, we are in question 4. I just go briefly with you. We almost finished already. Just a bit left, that's all. A small steel sphere is oscillating vertically on the end of a spring as shown in figure 4.1. The velocity of the sphere varies with displacement x from the equivalent position according to the equation, that one there, where v is in cm per second and x is in cm. Calculate the frequency of the oscillation. Compared to standard form, this is given by a formula sheet. And remember, go ahead. That one is omega. That one is x naught square. Compare. Omega is 9.7 by f. Then subject f. Omega. Put omega value divided 2 pi. Calculate out 1.5 first. Amplitude. Amplitude, use that. X naught square 11.6. And take square root. Find x naught. Calculate maximum acceleration a naught of the sphere. Right, that is the equation. Then 9.7 square the omega, then 3.4. Right, we use cm, so we get cm second minus 2. Then sketch the graph. Right, they ask you to calculate. So there's the equation. For this equation, there's a straight line passing through origin. And then make sure the amplitude is correct. And A not correct. A not correct. Okay, that's a marking scheme requirement to get a 3 mark. Describe without calculation the interchange between potential kinetic energy of the oscillation. Right? Sum of potential energy and kinetic energy is constant. At maximum displacement, kinetic energy is 0. Or at maximum displacement, potential energy is maximum. At 0 displacement, kinetic energy is maximum. Or potential energy is minimum. Either one. Okay, let's go to number 5. Two capacitors A and B are connected into the circuit shown in figure 5.1. Capacitor A has capacitance C, so capacitance C, and capacitor B has capacitance 3C, there's 3C here. The electromotive force is V, that one. Two-way switch S is initially at X, and capacitor B is initially uncharged. Right? This one is uncharged. We put a switch here, this one is charged completely. Say in terms of V and C, the expression for initial charge on the plate of capacitor A. How do you calculate?
This one is the Q equals CV.
Q equals to CV. Initial energy, what's the formula?
Half CV square.
Half CV square two-way switch is now moved to position Y state and explain what happens to the charge that was initially on the plate A. Yep. Happen to the charge initially at this at A.
So the charge on A is transferred to the plates of capacitor B because PD across capacitor are not equal.
Some of the charge transfer to plates of capacitor C, B. Transfer is because the PDs across the capacitors are not equal. The transfer stop when PD across capacitor is equal. Okay, so the charge at A is transferred to B until the PD across both of them are the same. Then the charge stop moving. Show that the final potential difference across B is given by VB equals to V over 4. Explain your reasoning. Right? As we have already argued out, final VB equals VA. Finally, then the final charge QA plus QB equals to initial charge CV. Right? Conservation of charge. Then replace it with VB. And then this one B 3C times VB equals CV. C can cancel off. So VB equals to 4 over V over 4. Determine the expression in terms of V and C for change in energy of total energy that is stored in the capacitor as a result of change in position of the capacitor. Right? That's the initial energy stored. Final energy. Right? These two are now parallel. So 3C plus C is 4C. Right? C and V is that one there. Final voltage is V over 4 square. Then cancel by 2. 2 times 2. Then cancel this 16, cancel by 2. That one becomes 1. This one becomes 8. So CV square over 8. Right? Initial minus final. Okay. Why is the difference in energy? Why is the difference in energy? Why is there a difference in energy? Yep.
Wait, what did you say?
Why is this? There's a difference in final energy and initial energy.
There's a Can I see some energy being converted to heat energy, thermal energy?
No, when the charge flow, energy is lost in the wire. Okay or not? Yep. When the charge flow,
Lost in the wire due to what?
motion. Just like current flowing through
Oh,
wire, there's
oh
resistance.
yeah, energy. Yeah, shit. Oh yeah, okay.
Energy is lost in the wire as heat. Right? These are things you need to remember for electromagnetic induction. Just like looks like it's coming out very popular. Right? Before that, magnetic field and electromagnetic induction are separate topic. Now they are combined into magnetic field. So magnetic field used to be popular from 2022 Now it's electromagnetic induction, right? No, right? The definition. Anti-flux linkage, Faraday's law, and then Lenz's law, right? And then this is the gradient of phi over t graph. Okay, a heavy aluminum disc has a radius of 0.36 meter. The disc rotates with the wheel of a vehicle and forms part of electromagnetic braking system on the vehicle. In order to activate the braking system, a uniform magnetic field of flux density 0.17 Tesla is switched on. Active field is perpendicular to the plane of the rotating disc as shown in figure. Right, that figure. Define magnetic flux, okay? Without looking at your answer. Define magnetic flux.
Product, hello?
Yeah,
Product of magnetic flux density and area normal to magnetic field.
okay. Calculate the magnetic flux to the disc. Give your unit for your answer. Okay. What should I do? How to calculate?
Then use the phi equals bx pi r square. And BA,
Consider it one round. No?
B
So you
square,
area of
yeah.
the rotating disc. No? So that's your BA. There's your B. There's your B. And pi radius. Pi r square. And then it's in Weber. The disc is rotating at 25 revolutions per second. Calculate the magnitude of electromotive force induced between axle and the rim of the disc. Time for one revolution is 1 over 2 of 25, divided by 0.04 seconds. Right? Supposed to be differential, but yours is not calculus based. So they accept shortcut. Right? There's a change in flux in one revolution. There's a time. Okay.
Okay.
The axle, the rim are connected into an external circuit that enables the energy of the rotating disc to be restored for future use. The direction of rotation is shown in figure 6.1. Okay, that's your figure. Use Lenz's law of electromagnetic induction to determine whether the current in the disc is from the rim to the axle or from the axle to the rim. Explain your reasoning. Okay. How to decide?
Force act on the disc because current in the disc is perpendicular to magnetic field.
I think it's 3-mark question, so you have to give 3 reasoning. 3
And
points.
then force opposes rotation of the disc by Lenz's law.
Current in this is perpendicular magnetic field. That's important, the first point. Or current causes force to act on the disc. Okay. That's Lenz's law. current causes force to act on the disk. Force oppose rotation of disk. So this is going clockwise. So if the force is to the left, instead of to the right, it's going to the left. Force oppose rotation of this, then you use Fleming's left-hand rule. Fleming's left-hand rule. Okay. Any comment?
Wait, Andrew.
Okay.
Uh, wait, give me a moment.
There's a force. There's a field.
Okay.
There's a current. Fleming's left-hand rule.
Mm.
There's your field. There's your force coming out. Your field is going to the left, going to the right, sorry. And your current is going down. Then
Okay.
time is the force of the thrust. All diodes are used in the bridge rectifier circuit to produce a rectification of sinusoidal AC input voltage Vin. Figure 7.1 shows part of the circuit, but 3 of the diodes are missing. The PD across the load resistor R is output PD, V out. Right? There's a V out of the bridge rectifier. State the name of the type of rectification produced by the bridge rectifier.
Full wave.
Okay, full wave rectification. And it's up to you to draw lah. This one. Right, the two arrows are parallel, pointing the same direction. These two, two same direction. And at the junction there, that's your V in. V out is where the arrow point. Important here. Okay, you're not sure, check it out. V in positive, current will flow this way, and then cannot go out this way, will go this way, and flow back here. Right, when this one is positive, it flows this way, go out here, go there, go back. Okay, that's a marking scheme. Okay, that's what we have done previously. V in has amplitude V naught and period T. Figure 10.2 shows the variation with time of V in. On figure 7.3 sketch the variation of V out with T or T equals, right? That's your input. Output will follow, except the negative becomes positive. That negative becomes positive. Okay. That's how you get your 3 points. Then you look at V naught, look at maximum at this point, maximum at this point, at that point there, and then minimum somewhere halfway, halfway. Power dissipated in the resistors is P. Sketch the variation of P with T between t equals 0 and t equals to 0 seconds. So basically it's the same as previously. Right? Remember that V naught square over R. Okay, same. That's how they will mark you, give you your 2 mark. Any comment?
Okay.
Okay, not comment. Let's carry on. Suggest you reason how the root mean square value of V out compare with the root mean square value of V in.
Uh, V square, the V square against time graph is the same for both V out and V in. So the root mean square are the same value.
Same power time graph with or without rectification. So same root mean square. Or V square against time graph is the same for V out and V in. So same Vs. So these are alternative answer. Okay, for energy level, which is becoming popular, right? Remember that this is the lowest one is minus 13.6 for hydrogen. Don't worry about this one. Don't worry about this one. This is the ground state. Visible one is the second level. And then that's how you calculate your energy of photon. Is the difference between the energy level. And then a longer wavelength is further apart. Right? Follow here. This is the emission spectrum, absorption spectrum. This is roughly the same. Right? That one and that line the same. That one and that one the same. This one will give out the green line. And this one will give the blue. This one will give the violet. Okay. Figure 8.1 shows 4 energy levels of electron in an isolated atom. Right? Remember the energy calculation formula? Figure 8.2 shows lines in the emission spectrum of atom that correspond to transition of electron from N3 to N1 and N4 to N1. And remember, they are very close together. That's why you see these two very close together. Explain with reference to proton why this single frequency of electromagnetic radiation that corresponds to each of these transition. Okay, you want to try?
Mm.
Yeah, can.
Uh, let me see what I wrote.
Basically a summary of by this formula. Transition emits one photon, right? Whether from N3 to N1 or N4 to N1. Emits one photon with energy equal to the difference in energy between the two levels. Right? Energy between the two levels. Frequency of radiation corresponds to the energy of the photon. That's all. On figure 8.2, four lines that correspond to transition from N2 to N2 to N1, to N1, which is N1, no? N2 to N1, right? N3 to N1, so it's quite far away lah. That's how you draw, right? Roughly correspond to that lah. On figure 8.2, draw a line that corresponds to transition of electron from N3 to N2. N3 to N2, distant there, that distant there. Right? Smaller frequency, right? So it's far away. There's a B. That's the marking scheme will say that. How you get the mark. Okay, any comment?
No comment.
Okay. Yeah, all right, let's carry on. Frequency of radiation represented by line A is FA, that's your FA. Frequency of radiation represented by line B, FB. Energy of ground state, N equals to 1, E1. Determine an expression in terms of FA, FB, E1, and Planck's constant for energy E3 of the energy level N3. Okay, you want this one in terms of E1, FA, FB. Right, the two equations. Right? Higher energy level minus lower energy level equals to H times frequency. H is Planck's constant. So E2 minus E1 is HFA, equation 1. E3 minus E2 equals to HFB. And you add the two together, two equations together. Right, eliminate E2, so that E3, E1, HFA plus HFB. Then take this one across there, there's the answer. Okay. Any comment?
Okay.
Okay, define mass defect. Yep. Can all this must be very
Difference between mass of nucleus and the total mass of nucleons.
Difference between mass of nucleus and total mass of nucleons when infinitely separated. Table 9.1 shows a mass defect of 3 nuclei. Nuclear fusion process in a particular star is given by the equation. We've got 10 more minutes. Where X is a particle that has no mass defect. State the name of X. You can work it out, or most likely it's a neutron. Work it out, you can say conservation of nucleon number. Okay. At the top there, left hand side and right hand side must be the same. That one is A. So A is 1. Then the conservation of charge. 1 plus 1 equals 2 plus Z. So Z equals 0. So it's a neutron. Particle is a neutron. They don't expect you to do all this. Can guess it straight away, but if you cannot guess it, then work it out. they won't give you extra mark lah. Show that the energy released when one nucleus of helium-4 is formed in a fusion reaction is 2.8 times 10 to the power minus 12 joule. Right? Mass defect.
Our recommended target weight is 1.
Mass of helium minus two of them lah.
Master control is okay. Master is enough.
Right? Atomic mass unit. Then change it to use delta M over C square.
In organic salt,
Atomic mass unit. Change it to kilogram. Right? One atomic mass unit is 1.66 times 10 to the power minus 27 kilogram. You can check our data sheet. This is the speed of light. Okay or not?
Okay.
The star in B has a radius of 2.3 times 10 to the power 9 meter and luminosity 1.4 times 10 to the power 38 watt. All the energy released from the formation of helium is radiated away from the star. All the energy that is radiated from the star has been released in the formation of helium-4. Determine the mass of helium produced per unit time by the fusion process. That is your luminosity L. Total power lah. There's a number of atoms. That's the energy released for this reaction. So you want to find N over T. Right? So L cross multiply L over delta E. Put in your value, number of atoms per second. Right? That's your L. Right? That's your delta E. Calculate out. Mass of one atom of helium-4. There are 4 nucleons there lah. So 4 times each nucleon has an atomic mass unit in kilogram. So that is your mass of helium-4. Right? Basically, just take this number, which is the number times this one. Okay. Any comment?
Okay.
Surface temperature of a star. What formula to use?
It's the L equals 4 pi. What's the symbol
Okay.
for?
That is your formula sheet. L. Right? Real. Subject T. And then you get the equation. Put in your value. Right? That's your L. 4 pi R square. That's your R. That one is from your formula sheet. Data sheet for sigma. And calculate out. Okay.
Okay. Teacher.
Right, this is production of X-ray lah. Just summarize for you the things that have come out before. We have done that. Contrast is contrast SWOT. And this one radioactivity. Forgotten the formula. Just replace it with I. Right? I not I. Then energy of electron that's being accelerated. Then if all the energy is converted to X-ray, that is a minimum wavelength of X-ray. Right? This is your
teacher.
yep.
Hey, teacher, can we end the session after this? Because I have to study for like my papers.
Oh, okay. So we end this lesson now. Okay.
But we can move it more frequent on let me check.
Say again.
The session you can just move it to move it more frequent in the close May 7 onwards. May 7 onwards. Wait.
7 the next month now.
Yeah.
So you want the class next week or not?
Wait, let me see. Yeah, next week I have one class.
You tell me lah. You confirm with me lah.
Okay. Yeah.
Actually, for use in medical diagnosis are produced in X-ray tube. In X-ray tube, charged particle accelerated towards the metal target by and apply potential difference. State the name of the charged particle that are accelerated by the PD, by the applied PD. Yep. Why is it being accelerated?
Electrons.
Electron, okay. Explain how X-ray are produced at the metal target. Yep.
When the first moving electrons hits the metal target, they are decelerated rapidly.
Okay, electrons are decelerated on impact with the target. Kinetic energy lost by electron emitted at X-ray. Calculate the minimum wavelength of X-ray produced when an applied PD is 5.80 kilovolt. Okay, that's the energy of the electron converted to a photon or X-ray. Right? Subject your lambda, put in your value, Planck's constant, speed of light, charge on electron, potential. Okay. X-ray pass through medium has an attenuation coefficient of that. Calculate the percentage that is absorbed in cm thickness. Right? Use radioactive formula, except convert to X-ray. Right? That's percentage transmitted, percentage absorbed. Okay. Any comment?
Okay.
Anytime we cut off already. Okay, so we end it here. Good night.
Yeah. All right, good night, teacher. Do you want me to send you the timetable?
Can also if you want to.
Okay. All right, thank you, teacher. Good
Okay,
night.
good night.